Okay, we'll share screen soon. Yeah, before we start today's, good morning, today's program, about your question, Aniruddhan, concerning that that last thing we looked at. See,
Yeah.
instead of that the Poisson process with random intensities. You asked a question, no, heuristically, why? What is the explanation for?
Yes.
See, the thing is, instead of let us say Poisson, that is the arrival rate being fixed. That is, if it is a fixed rate, that is lambda, then we know it is a homogeneous Poisson process. Then all nice properties arise. So just for example, suppose there are, it is to be unknown parameter, it is to be, let's say, between lambda 1 or lambda 2. Let's say even with equal probability, half. Even then the behavior changes drastically. You sort of go through the, even simple computations. So now, that is, or if it is lambda 1 with probability p and lambda 2 with probability 1 minus p, then again the expected things, what you have seen in homogeneous process, doesn't happen. So basically, this is a convex combination of two processes in some sense, right? And if your that parameter is a random variable, and then you have to later integrate with respect to that, that is also a convex combination. Integration with respect to a probability measure can be viewed as a convex combination in a continuous fashion, right?
Yes.
So, I mean, it would be too greedy on our part to expect that many nice results of the, which we had seen in the homogeneous case, should continue to hold, even though that integrating thing measure is a exponential distribution. What I'm trying to say is that the homogeneous case, we have started with fairly nominal assumptions and then arrived at the process. So that is kind of one in a kind, in the sense that that is a reason why Poisson process seems to be prevalent in nature. So that kind of miracles, I think it will be too greedy for us to expect to happen every time. Okay. So in other words, one would have been surprised had that some of the nice properties, that independent increment, etc., carry over even in this case. That would have been a surprise. Rather, the default expectation should not be that it should be all the nice properties should carry over. Okay. I mean, when one sees a lot of nice results, one expects many nice things to happen, but sometimes it doesn't. Okay. Anyway, yeah. So let us go to, now today's. Yeah. So today we will start with compound Poisson process. This is an important class of processes. A continuous time stochastic process, let's say xt, is said to be a compound Poisson process if it can be expressed in this fashion. Xt is summation I going from 1 to nt. Of course, nt is going to be a homogeneous process, yi. So it's a kind of random sum where this NS is a time homogeneous Poisson process. And of course, these YIs or YLs is a family of or sequence of IID real valued random variables. So this is a process built out of a homogeneous Poisson process and an IID sequence. There is one more condition. If you want to note it down, please do. Of course, we will make one more assumption that again you can perhaps expect. This process N and this family YL are independent families of random variables. Again, this kind of assumptions are made to make things mathematically amenable and also as a first step in trying to analyze some sort of unknown situation. Certain assumptions are normally imposed so that the resulting object becomes amenable to mathematical analysis. So please note down, it is a compound Poisson process. If it can be, it is in this form, a random sum of the IID random variables, and the random parameter is governed by this time homogeneous Poisson process. And these families are two independent families. So this equation, of course, this here we don't show the random parameter here, that is that little omega. So what that basically denotes is that for every t non-negative and omega in capital Omega, the basic probability space. So this is xt omega. It is also, it can be written in this fashion. It can be written in this fashion. It is written here to denote that we are considering t as being fixed and as a function of omega. When we write here, we are sort of suppressing this parameter, it's understood. So this is obviously this y I summation yi omega, I going from 1 to nt omega. So for different omegas, you may have nt omega can be different, and therefore this also can be a smaller or a larger family. So this denotes y1 omega plus y2 omega up to y sub nt omega at omega. Be careful in writing. And of course, what it means is, if you remember that the nt can possibly be 0. If no arrival has taken place till time t, nt omega will be 0. In such a case, this sum would be interpreted as 0. Though here we start from I equal to 1, when this itself is 0, it is usually taken as 0. And of course, if it is nt omega is integer k can be any positive integer, then it will be y1 omega plus y2 omega plus yk omega. So this k here plays the role of this n sub t nt omega. Please note it down if you want. Okay. So compound Poisson process, they are used to model a large variety of situations. And arrivals, of course, occur in accordance with a homogeneous process. And each arrival has a randomly determined value, cost, or reward associated with it. That is, these yi are the rewards or cost, etc., associated with the ith arrival. Or, yeah, cost or some expense. This determined value need not always be in terms of money. It can be perhaps certain other kinds of quantities, the amount of damage done and things like that. Amount of damage done, not necessarily in monetary terms, but in some other fashion. So generally it will be assumed, I mean, YIs can be positive or negative, but we will generally consider the situation when they are positive, and we will generally assume that probability of YL taking the value 0 is 0. Obvious reasons, because if some arrival, it going to entail only 0 cost, and that probability is significant, I mean, is positive, then that can complicate matters. Then you will have to consider those arrivals for which the cost is non-zero, and for those things it is 0 and so on. Okay. So now note that, yeah, here both depend on omega. So now, see, you know that nt omega, or for a fixed omega, it has discontinuities at certain points, namely the arrival times. So let us say in between the arrival times, for fixed omega, nt is a continuous function. You can easily see from this definition here, the same thing is true of xt also. Since we are also assuming that yi is, I mean, with probability 0 only, they take value, 0 value. As long as there is no new arrival, xt remains the same. So these, for a fixed omega, the sample path, that is the trajectory of n, the homogeneous process corresponding to omega, and the corresponding sample path of x for this fixed omega, they have discontinuities at the same points. And those points are precisely the arrival times associated with this omega, or TJs. Also, it's clear that the jump, of course, these will be jump discontinuities. This jump of n at any discontinuity is +1. Again, you remember that n keeps on increasing, or rather non-decreasing. So at any tj, the discontinuity amount is +1 for n. And for x at tj, it will be yj omega. So in other words, the compound Poisson process generally does not create new discontinuities in the sample path behavior. That is the behavior of the trajectories. Of course, since yi's can possibly be negative also, this can turn out to be positive and negative. Whereas n is an increasing thing, non-decreasing process. Okay. Okay, now we will prove a result. Okay, please note it down. 1, 2. All right. We will prove a theorem now. A compound Poisson process xt has independent increments and also is time homogeneous. Okay. All right. The proof is not difficult. So in our definition, the first two assumptions, namely n is a homogeneous Poisson process and y are IIDs. So now look at time t1. Probably it is better to have this thing in front of you. At t1, so that the random variables which you have at time t1 are nt1, n at t1, and also y1, y2 up to y sub nt1. These are the things which are going to build up xt1. So we want to show that things, they have independent increments. Now, suppose you take xt2 and xt2 minus xt1. That will involve all these things between t1 plus 1 and t2. So in that case, you have nt2 minus nt1, of course. In addition, you have t sub 1 plus 1, t sub 1 plus 2, etc. up to y sub t2. So that is what is involved here. So we have this, take out these groups. These are the kind of building blocks for the xi's. So y1 up to y sub nt1 and also nt1. You can even put this nt1 first and so on. These things we know are independent. Once t1 is fixed, this is a number, nt1 is a number. So these are IIDs, and we have this. You cannot say that nt1 and y sub nt1 are independent. Because the very nature here, this depends on what the value of nt1 is. Then in the next thing, it is y sub nt1 plus 1 up to y sub nt2, and similarly here nt2 minus nt1. Now we know that nt1 and nt2 minus nt1 are independent random variables. And if supposing nt1 is 3 and nt2 minus nt1 is 5, this will have y1 up to y3. Here it will be y4 up to 8. And these guys and these guys, they are IID random variables. And we know this and this are independent. So consequently, you can easily see that this, the first collection and the second collection are independent collections. Is this idea clear? So similarly, you can go up to any finite k. So dot 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 up to y sub ntk minus 1 plus 1 up to y sub ntk and ntk minus ntk minus 1. These are independent collections. The first collection is independent of the rest, and so on. And this one is independent of each of the previous. Any of them is independent of the others. Of course, this does affect this. So this collection and this are not quite independent. But if you are given some value here, nt, if this thing is equal to some 15 or something like that, then those 15 random variables which occur here, but then the normal, this thing will be different. It will be some particular numbers. Then those guys will be different. That kind of a thing will follow because of our assumption 3. Okay. Consequently, xt1 minus x0, which is the sum of those first collection, xt2 minus xt1, which is the sum of the things in the second collection, and xtk minus 1, which is the sum of the y's in the last collection. These are independent random. This kind of a thing follows from what you have seen in your probability course. If, let us say, x, y, and z, x comma y, the two random variables, let's say, and z and w, x, y, and zw are independent two-dimensional random variables, say, that is x, y is independent of zw. Then any function of x, y, and any function of zw are also independent. This kind of things you would have used in your probability statistics courses. You would have seen things like x1, x2, xn, and y1, y2, ym are independent families. Therefore, take the sum of the squares, they are also independent. All the xi squares and all yj squares, they are two independent random. Things like that. The same thing is done here.
Sir, one quick question. So here we are not demanding that the yj's are natural valued, right? So they can be real valued.
Pardon?
Here we are not demanding that the yi's are yi's take values in natural numbers, right?
No.
Okay.
No, we don't demand.
Okay.
As a matter of fact, in many contexts, we will be assuming they are continuous random.
Okay.
Because many applications, that seems to be the way it arises. So as we had indicated, this YIs can denote some cost or some value and things like that. If one demands that these things should be integers, that might be too much of a restriction. Of course, you may say that instead of integers, you can allow, let's say, all let's say, a certain amount of fractions and things like that. But again, the unit you choose, as long as it is allowed to take only countably many values, the unit you choose is not this thing. See, in our earlier course, we had time also discrete, but here we are taking continuous time. But then certain times only the interesting events occur, like the arrival of claims and things like that, or arrival of some events, or arrival of shocks, and so on. And each such arrival entails certain numerical measure value. So the process xt has independent increment property. So this is another reason why compound Poisson process are also turning out to be a nice structure, I mean, more mathematically amenable, because independent increment property is carried over. Okay. Now, to show that xt is, please note down. To show that x is time homogeneous, we need to show that is the xt plus x minus xt. Here the time points differ by age. And the distribution of that, probability distribution of that random variable is same thing as x at age. That is stationary increments. A similar reasoning we will apply. Now we know that nt plus h minus nt has the same distribution as nh, because our process n is a time homogeneous process. So this is precisely the follows by that postulate n4. Note it down. also, well, okay. Why, say, supposing NT is some particular value to take 5 or something like that. T is equal to 5 and T plus H is 7. So this will be y sub 6 and y sub 7. So the time difference between T and T plus H is 2. So y1, y2 here it will be. So this we know by, since YIs are IIDs, we know that, let's say y6 and y6, y7 has the same distribution as y1, y2. Because in the computation of this, that will be involved in addition to this. So the same kind of reason which we had used in the independent increment property proof, part of the proof. So y t plus x minus xt, that is the sum of these guys, that is independent of, sorry, has the same distribution as the sum of these guys. Of course, here these two intervals can even overlap. Only thing is that this difference should be same. T can be, let's say, NT can be 5 and N6. The other one can be N4 and N5. Even then, this. So this completes the proof, and I think I will stop here for the day. Also have to attend to something else. And next thing is want to consider the distribution of the random variable xt in terms of the other quantities. So that I thought I will do it at one go. And concerning your portion, I think most probably whatever we did till last week for the midterm. So this compound Poisson process will spill over to next week also. So if you want me to go over any of the previous slides, please tell me.
So this one question.
Pardon?
So just one question. So here, since we're not assuming yi are natural number valued, so we also need something for the not more than 2 events will occur in one interval. So will that be reworded? Or?
Pardon, can you repeat the question?
So here we're assuming that the yj's are in arbitrarily real valued random variables.
Yeah.
So do we need to reword the N5 and N6 criterion?
N5 and N6?
The N5 and 6 criterion. That is not more than one event can occur and things like that.
Now you mean to say that, but see the number of events that is determined by n, no, arrivals.
Yes, yes. No, here you're claiming X to be a Poisson process.
Pardon?
You're claiming X to be a compound Poisson process.
Compound Poisson process is just a terminology given.
Or just dependent on n simply because.
Yeah, it is something which is built out of Poisson process.
Oh, okay.
Compounded.
Okay.
I mean, in that sense, okay. I
Okay.
mean, so it is something compound Poisson process. It is something built out of Poisson process. One has to give a name. So this compound Poisson process will in general be not a Poisson process unless you, as you said, the YIs take integer values and also always positive and things like that, and also same kind of values, so that you have various properties. I mean, it will more or less amount to assuming that the YI is constant.
Okay. Got it.
Okay. So in that case, it might just turn out to be some kind of a multiple of NT. Supposing all the YIs are equal to 3, then you would be considering this will be just 3 times NT. So which is, as you know, it's going to be a Poisson process with instead of arrival rate being lambda, it is 3 lambda or something. Yeah, even if these are, what is it? Take only non-negative integer values, in general, this will not be a Poisson process unless you make that a constant. See, the thing is, the objective is to try to study as many phenomena as possible using the kind of tools available to us. So let us say one has Poisson process, homogeneous Poisson process. So that might have been, let us say, formulated in certain context. You come across some other phenomenon which one would like to analyze. Then if one realizes that the changes in that thing, let us say XT is something which occurs in some study of something else, some other problem, some other discipline. You observe that the changes in this XT value occurs at times which can be modeled by a time homogeneous Poisson process. So then what happens? Can that be studied using whatever information which we have concerning Poisson process? I mean, the objective is not just to study what kinds of processor are similar to Poisson process or time homogeneous Poisson process. The Poisson process is, let us say, nature has presented us with. It is a process with very nice properties. So with that as a tool, what all things can one study? Which can be made use of in many cases. And compound Poisson process turns out to be one such. So that happens to be reasonably versatile. Actually, maybe from the end of this week or beginning next week, we will concentrate on its connection with the insurance model. And similarly, certain other fields also you can do. So when you have a nice tool like Poisson process, it is this thing is based, since we know that, and also an observation that here certain things seem to, the changes in this thing follows the Poisson process. That means the changes means the arrival of new things. So why not try to model it in this fashion, and then use it. Use the information concerning Poisson process to advantage. And also it always be, I think it is, one should keep in mind that many of the pure maths or abstract math things have come from applied sciences. As you know, the entire analysis have come from the study of, more or less, I would say, differential equations, which in turn has come from our study of physics, how to quantify or do quantitative study of things in nature. Of course, once a particular kind of subject develops its own tools, then one can pursue that for purely its own sake, to see what all things can be developed out of that, which in turn might prove to be useful later on for studying some problems in coming from applications. And also certain kind of applications, if this thing is there, you also know what kind of results one can expect, because of such things have been observed in practice. So that will give you some kind of a, to make the appropriate guess. Or some interesting connections, even between two fields of maths. And so, okay, so I will stop sharing now. And oh, today you seem to be the lone participant. Anyway, our thing is going to be like that. Okay. Okay. So we will.
Thank you, sir.
Yeah, we'll meet again on Wednesday.
Okay. Bye, sir.
Yeah. Bye.